Okay. Our topic today is software reliability, or software engineering, or the social implications of computing. And we're looking at a case study which is the most famous computer software disaster, the most studied disaster ever, although not the worst, actually. But the worst that we really understand very well, and that's the Therac-25. So help me out. Who actually read the paper? Oh, good. All right. So I can pass quickly over the background. The Therac-25 was a therapeutic X-ray machine that's different from the diagnostic ones that you've all had applied to you probably by now. It's much higher radiation intended to burn out a cancer. So this machine had 6 occasions when it accidentally delivered a huge overdose of radiation. 4 of the patients involved died. The other 2 were very, very severely injured because of software bugs. And if you're me, the first thing that comes to mind when you hear that story is, well, let's not write software like that. But that's not a good answer, because the Therac-25 also saved hundreds of lives of cancer patients for whom it didn't overdose accidentally. So it would be even worse not to do it than what happened. But what happened was bad enough. Yeah?
So were there only 6 known cases of overdose, or are those the most severe ones?
No, there were only 6 known cases of overdose. Yeah, most of the time it worked great. And the machine that it replaced, the previous model, worked without failures. So the company had a long history of successfully building these machines. But this particular model was not successful in that way. And I hope you got the point from the article, and I really want to emphasize that this is not a story about bad guys who, callously put profits ahead of lives. There are plenty of stories like that. The canonical story like that is the Ford Pinto. Who knows the Pinto story? Very few of you. Okay, this is before you were born. The Pinto is this little car made by Ford, and it had the problem that if you rear-ended it, there was a very good chance of the gas tank exploding. But what's interesting about this story is that Ford engineers figured out that they had this problem before there were any actual explosions. The Ford engineers went to the Ford management and said, look, we should recall these cars and fix this. Management said, no, it would cost too much. Okay? So they got sued for hundreds of millions of dollars, and lost the case deservedly. So that's a story with bad guys. But the Therac-25 story has no bad guys. Everybody involved really wanted to save lives. That's what they were there to do. And so this is, instead of being a kind of morality play story, this is a story about how hard it is to build software, large-scale software that works. Why is that? We understand a lot about the process of engineering. And engineering software, if you look at it sufficiently abstractly, is just like engineering anything. But actually, it's very different, because the other engineers work with material things, and those things have known limits. So hardware, rusts out or wears out, or the battery stops being able to take a charge and stuff like that. And software doesn't have that kind of degradation to it. And it also doesn't have the limitations that you have when you're physically building things. Footnote. Hardware people are getting to the point where they can build things on the level of complexity of software because they do their building in software. So now they're building electronic circuits where a switching element can be a single molecule. And once you're at that scale, you can build very, very, very complicated hardware that has the same possibility of failure as the very, very, very complicated software does. But with software, there's no limit to how big a thing you can build because it doesn't take any physical space, doesn't use any, iron or steel or selenium or whatever. And so the sky's the limit. And that's why, even though software doesn't degrade, it still has more problems rather than fewer problems than hardware. So if you think about bridge building, you can probably count on your fingers how many bridge failures there have been in recorded history. Right? Yeah, there's the Tacoma Narrows. Now, who can name another one? Right? And that's because there's only so many ways to build bridges, and the bridge engineers learn them, and they design conservatively, and so things, by and large, work. It's pretty amazing that computers actually work pretty well. When the first Intel Pentium came out, I don't know if you know this story, there was a bug in floating point division. So certain problems, you get slightly wrong answers. And this happened because they put the machine through rigorous testing and rigorous analysis, and it was completely right, and it passed. And right before they started building them, some engineer figured out a kind of shortcut, a way to speed things up in the division algorithm. And unfortunately, that way to speed things up didn't actually work. So it was a last-minute change that made the hardware not work. But we just expect software not to work. It's different from bridges, right? I mean, when you use a computer, every so often you get the blue screen of death or the spinning beach ball of death or whatever it is, depending on your operating system, but there always is one. And you just say, oh, well, that's how computers are, reboot, right? Bridges aren't like that. Rockets aren't like that. Airplanes aren't like that. You can't reboot an airplane. People expect them to work every time. So why? Because software is hard because there's no limit to how complicated it can get. That's sort of the big first thing to understand is we build these massively complicated programs, way more complicated than anything hardware people can do. So that's where we run into trouble. Oh yeah, I'm supposed to tell you the Star Wars story. Who knows what the Strategic Defense Initiative is? Oh, a lot of you, good. This is like back when Reagan was president, so what, around the time you were being born, more or less? They said, we are going to protect the United States with an invisible shield of satellites in space that will detect and shoot down any missiles that might be aiming at us. And this software, these satellites are going to have, weapons of mass destruction in them that can be used to shoot down these missiles. And they're going to be entirely autonomous. Well, the program that they were going to write to control these satellites was about 10 times bigger than any program that anyone had ever written before. So a bunch of computer scientists said, this is going to be a disaster, right? And we can't let this happen. And so they did things like testified before Congress about what a bad idea this was. And that was the beginning of an organization called Computer Professionals for Social Responsibility, which was modeled after a group called Physicians for Social Responsibility, which was an anti-war group. Their focus was on war as a public health hazard, which of course it is. But CPSR's focus was on computer systems as a public health hazard, basically. And there was a lot of reason for them to be terrified, because this was back in the days when there was the US and the Soviet Union were the two big powers pointing missiles at each other, and each side had enough nuclear weapons to blow up the world 100 times over or something. It was really ridiculous. And there were, it turned out later, we found out, dozens of occasions on which World War III almost started because some computer thought we were under attack, or they were under attack. They had their dozens too. You know, we know more about our dozens. And in every case, the supposed attack turned out to be a flock of geese, or just some random airplane, you know, or just plain a radar hardware malfunction. And the reason we didn't have World War III in each of those cases was that a human being the protocol for starting World War III required a decision by human beings. So the computer would raise an alarm, and then some human being would look at it, and the human beings, thank God, said, oh yeah, I've seen this situation before. It's a flock of geese, and not push the button. But now they were going to have these satellites push their own buttons. So that was the first time that the issue of software complexity really came to public attention as, you know, something that really, really mattered. Well, not many of you are going to end up working on software projects that are explicitly life and death. Right? You're not going to be working on therapeutic X-ray machines. I hope you're not going to be working on automated weapon systems. So you might think that this doesn't apply to you. But you know, in my notes it says there's a continuum from Therac at one end that's obviously life or death, and video games at the other end that are obviously not life or death. And then there's stuff in the middle, like operating systems. At one point, the tanks in Iraq, the US tanks in Iraq, were running Windows. This was a long time ago. They were running like Windows 2000 or something, you know. So that was life or death, and it wasn't, you know, the people who wrote that anyway. Today, this is a change from my notes, things keep changing. There's nothing, no job you can do about which you can say, thinking about the safety of this program doesn't matter. Let's say you're writing a video game. Today, that video game is almost certainly web-enabled, right? And that means that other people on other computers whom you don't really know are going to do things that affect the running of your computer. And so your software, even if it's game software, has to be written in a way that's going to not do any damage to your system, even in the face of deliberate enemy attacks, right? I don't mean by enemy like enemies of the US. I mean, you know, some teenager in Finland who wants to break into your computer. So everything, software reliability of everything now matters because of the net. Okay. So what went wrong in the Therac? And this is the meat of that article that I asked you to read. And there were so many different kinds of things that went wrong. And here are the ones that I found. No atomic test and set. So this is the thing we were just learning about a week ago, that the software was multi-threaded, or there were external events that would cause it to jump to do something else. And critical sections were not protected. Now, as you know, when you have that kind of bug, most of the time it works, because most of the time you don't have these two conflicting things happen at exactly the same time. And that's why most of the time the Therac worked, right? Because this kind of concurrency bug didn't happen except once in a while. Hardware interlocks removed. That was a cautionary tale. If you remember, the previous model Therac was really running essentially the same software, but it had a little hardware widget, a limit switch, mounted on this turntable that controlled the aiming of the X-ray, that would make sure mechanically that certain combinations of settings couldn't happen. The software was also checking for that error. So somebody said, you know, we can save a couple of bucks per machine by leaving off this hardware, because the software is doing the job for us. So a very important lesson of that is redundancy. And I want to really underline that, because in 61A, we always tell you, don't do error checks. Assume that your input is correct. And we do that because we want to simplify as much as possible the examples in this first course. But I'd like you to know that in the real world, you should put in error checks. Even when you think that some particular kind of error can't possibly happen, check for it anyway. By the way, when an error check does detect an impossible error, you have to tell some human being about it. Right? So they found out afterwards that those little mechanical limit switches on the old model Therac were saving lives, you know, month in and month out, saving lives by silently preventing overexposure. But it didn't ring any bells or, you know, print a message on the console or anything like that. It just silently fixed, you know, took care of the problem without fixing it. So make sure you have an audit trail of everything that happens, so that when a problem does come up, human beings find out about it and can diagnose it and fix it. There were a lot of user interface problems. So user interface is the subject of that Alan Kay video that we saw. Until relatively recently, people didn't think of user interfaces as part of computer science at all. You know, computer science is about algorithms. And how we deal with users, that's, you know, somebody else's department. So what did they do wrong? One example that actually was still the case in a lot of software that we used until pretty recently is there's the little arrow keys on your keyboard to move the cursor around. It turns out those things don't sort of hardwarily move the cursor around your screen. Those keys generate a sequence of characters that get sent to software, which interpret the characters as meaning move up, and send back a message to your screen, to your display controller, saying move up or down or left or right. Well, in the Therac, operators would fill out blanks in a form, the way you do in web pages. And they would, get partway through the form and then notice a mistake they had made higher up, and they would hit up arrow, up arrow, up arrow, up arrow, and the little cursor would move up. And then they would overwrite what used to be up in that line and think that they were changing a previous entry. What they were really doing was putting the string up arrow, up arrow, up arrow, up arrow, up arrow in this field down here, because that's how the software was written. So the moral is that what happens on the screen should correctly reflect what's happening inside the program. That was one user interface mistake that they made. Defaults. So if the operator is filling out that form and just hit return, enter on an item without saying anything, the software would assume some default value. Pretty common even today. And most of the time that's okay, but not when we're talking about therapeutic X-ray doses. In that kind of system, we've learned, you don't have a default. You make the operator enter a value. And finally, too many error messages. If you've used Windows, you know about this problem. If every time you do something, a little window pops up saying, warning, blah, 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 eventually you stop reading those things. You just click yes, OK. And that's what happened with the Therac. It gave a lot of error messages for situations that weren't really errors. And the operators came to understand this. So an error message would pop up. They would just not even read it. And then a different error message would come up that really was something important, and they wouldn't notice. They were just in the habit of hitting return. Documentation. This is probably the biggest problem. You ask any software company, is trying to get people to write documentation and have documentation that's readable. So you know how I keep thinking about Windows, but it's not just Microsoft, it's everybody. A dialog pops up and it says, how many Griebel flitzers per inch would you like? And there's a little question mark button. So you say, oh, good, I can get help. So you click help, and a window pops up that says, this screen wants you to enter how many Griebel flitzers per inch you want. And that's the help message. There were situations like that in the Therac too, where the documentation just didn't help people understand what was going on. And finally, and this is sort of the human interest part of the story here in the article, when these cases first came to light, nobody believed it. Right? The company that built these machines said, people use this machine all the time, and it, always works. If something went wrong this particular time, it must be that the operator made a mistake. Anybody ever heard that recently? This failure was due to operator error? People still say it all the time. Look in the news. Whenever you see some disaster involving computers, some PR person is going to say, this failure was caused by human error. Well, sometimes they were just wrong. It was a computer error. It was just an error that didn't happen very often. Other times, technically they were right. Technically, the human operator did something that he or she shouldn't have done. But the software was designed in such a way that it encouraged that kind of operator error by having bad defaults or by not behaving in the way that it looked like it was behaving, the things that I was talking about in the user interface. So one of the takeaway messages is anytime you hear somebody say operator error, you should be very, very, very skeptical. Because what that means is that some billion-dollar company is trying to scapegoat some $10 an hour worker for a problem in their system. So why was the company so defensive? Partly it's just human nature. You know, I say, you just killed somebody. You don't say, oh, okay, I'm sorry. You're saying it wasn't me, right? So that's part of the problem. And that has to be overcome. Another part of the problem is lawyers. Anybody going to be a lawyer when they grow up here? Really? Yeah. Oh. Okay, you can close your ears for the next couple of minutes. It's much, much harder for anybody to say, yes, I take responsibility for this situation, if the next thing that happens is they're going to be sued. How many of you drive a car? Right. In your mail, when you got your car insurance, you got a little pocket guide for what to do in case of an accident. And the very first thing it says is, do not admit responsibility. Right? Well, okay, that's a good way to not get sued, but it's not a good way to encourage responsible behavior. So that's a problem. And then, after the company finally said that they did have a problem, they fixed it. They found a bug, and they fixed it. And they sent out revised software. Glad that's taken care of. And then they had more failures. Right? So there were half a dozen independent problems that were found one by one. You know? So that's problematic too. So how do we fix this? I have an article that is assigned reading in my social implications of computers class that's from, well, it's about a company that does software consulting for NASA. They were building some software for the space shuttle at the time this article came out. And, you know, in that context, the software has to work the first time, right? It's no good to have a space shuttle take off and then discover a bug by the shuttle exploding. That's bad. So this company undertook to have software that worked the first time. And the article talked about how they did it. And there were some very interesting things. One was they treat writing software as a 9-to-5 job. 5 o'clock, you have to go home. You're not allowed to work all night. You know, none of these sort of hackathon-like sessions. Those things are a lot of fun, but they're not a way to get reliable software written. So you come in the morning, having gotten a good night's sleep, and you work your 8 hours, and then you go home, and you relax, and you have a good night's sleep. And they said that was one of the most important elements of their success at writing software that works. Another one is, and this is kind of, you know, painful to think about, nobody's allowed to write any code until they have a detailed specification. And I mean detailed. Practically every line in the software is documented. The documentation ended up being way, way bigger than the software. And they did all that first. And whenever you make a change in the software, you have to fill out a form in which you say what page in the spec authorizes you to make this change in the software. And somebody else reviews that to make sure that, you know, your understanding is the same as theirs. And then finally, what I think is probably the most important piece is that they built a climate in the company of not blaming people. People took responsibility as a group, and they worked very responsibly, and they understood the importance of what they were doing. But if something went wrong, the question they asked was not whose fault is this? The question was, what went wrong with the process? Because the process had a lot of redundancy in it. So nothing was supposed to get into the code that hadn't been checked by several people, and vetted with respect to the spec and all of that. So if a bug gets discovered, they want to know, how did that bug get past every piece of the system? And it's our responsibility collectively to improve the process. And that did happen. They did find some bugs, late in the debugging stage before delivering the software. And then they would go back and they would change the way they write software in response to how did this bug come in. So that's some of the background for what you have to do to write software that works. So more technically, redundancy is one thing, like that little mechanical widget limit switch. You can have redundancy in software too. You don't just check for something once. Every time it comes up, you check to make sure that you're looking at the kind of thing you think you're looking at. There's the notion of failing softly. That is to say, we'd like the software not to have any bugs at all. That's our goal. But let's say something does go wrong. There's some huge static surge through the system and the computer makes some random wrong answer. We want to ensure that if this system fails, it fails with the X-ray off, not with the X-ray on. So that's failing softly. Leave an audit trail. So this is a lesson that people have learned. All the time, your computer disks get full, right? You haven't done anything. You think, well, how can my disk be full? I had space yesterday, I don't today. What's going on? And what's going on is that all of those dozens of little background procedures with unpronounceable names in your system are writing records of every single thing that they do onto your disk. And every so often, you're supposed to go and delete the old records. And maybe the problem is that, like mine, your computer is sleeping at 3 in the morning at the time when it was supposed to do the deleting, so your disk filled up. But that record is a just-in-case thing. Just in case something goes wrong, you can look at those records. And ordinarily, nobody ever looks at them because they're way too much information. But when something goes wrong, then you do look at them. So that's the idea of an audit trail. And this is this notion of software engineering, which is the attitude of saying building software should be just like building bridges. Right? That's what software engineering is about. I always have fights with people about the teaching of computer programming to high school kids, because people want to instill good software engineering attitudes in kids. And I say, no, don't do that, because then they won't want to be computer programmers. Let them have fun and make mistakes. And when they get to college, that's when we'll teach them how to be software engineers. So here we are doing that. So there are 3 stages at which you can solve problems. The design stage, and then verifying you've written a program but you haven't run it yet, and then debugging. So design, modularization. So one of the stories about what object-oriented programming is about, I think I told you when we did OOP that you're going to hear different stories about this. My story was about a metaphor, about a simulation of something with multiple agents, and this programming technique being well matched to that metaphor. But another story is about information hiding. It's about if each object has its own local storage that's hidden and the other objects can't see it, that vastly limits the opportunity for one part of the program to step on something that another part of the program cares about. So that's modularization. The next one is understanding concurrency. So that stuff we did before about critical sections and serializers and all of that. The goal of us doing it, just as briefly as we did, is not that you're now ready to go into the world of work and not make that kind of mistake, but you're going to have more practice with it later. And when you hit concurrency issues in upper division classes, you'll say, oh yeah, I remember that idea from 61A, so I know what a critical section is. I know what problem we're trying to solve here. And there's the notion of analyzing invariants here in my notes. There's a homework problem. We didn't make a big fuss about this, but in the section on fast exponentiation, the theta of log n time exponentiation algorithm, and there was a homework question asking you to write it iteratively. And they give a hint saying that you have an extra input a to your helper function such that a times b to the n is invariant. Right? And what they meant by that was basically as b gets bigger and or n gets smaller, a shifts also so as to make it come out the same next time through the loop as last time through the loop. So that's an invariant, and you can design programs around things like that. You can say, you can put assertions in your code that say, according to my understanding of the situation, x plus y is less than 27 here. And in your debugging, you can actually have your program check. You can make that assertion executable. So if x plus y isn't 27, it gives an error message. Okay. So how do we verify that a program works? You've written a program. Some human being has written a program and handed it off to a computer. We'd like the computer to help us certify that this program is correct. So the first thing you have to understand is that that can't be done. Why not? Yeah. No, it's not because programs are really complex. Have you done the halting problem yet, that homework exercise? The one about suppose there's a program that checks whether another program halts? Okay, yeah. The checking program might be wrong. Yeah, that could be, but it's worse than that. It's theoretically impossible, even if we do everything as best we possibly can. If I hand you a program and its input data, and I say, I'd like you to write a program that will check whether this program finishes, never mind whether it gets the right answer, just whether it eventually terminates for this input. And your program should always terminate. Right? So it's easy to write a program that just sort of simulates the other program, and if that program terminates, this one will too, and if not, not. But we want a program that always comes up with an answer, yes or no, does this program terminate on this input? It can't be done. No computer ever will be able to do that. This was the first big, interesting result in theoretical computer science, worked out by Alan Turing, the guy who won World War II. He did. He won World War II all by himself by decoding the German Enigma cipher so that the Allies knew what the bad guys were up to before they did it. He also founded theoretical computer science, and one of the results is you can never, ever prove that a program is correct. So when somebody comes up to you and says, I've proven my program correct, you say, oh yeah, what about the halting theorem? But what you can do is you can prove certain restricted things about the correctness of certain classes of programs. And there's been a lot of work done on program proofs. And they have some very impressive results, even though we know for sure that they're not every possible bug found. We can still find lots of bugs and certify that certain kinds of bugs are not present. So the program proof people, what they like to do is they'll write a program checker, and then they'll take some big piece of public domain code, like Firefox is traditional, and they run their verifier or their program checker on Firefox, and sure enough, they come up with 20,000 bugs. And then they dig through the Firefox Bugzilla database, and they say, well, okay, 16,000 of the 20,000 somebody had already found, but we have 4,000 new bugs that nobody had found before that our program found. And that's how you know you have a good program checker. You'd think, since people have been doing this for like 1 or 2 decades, that Firefox would be totally bug-free by now, but it isn't. Not just because of the halting theorem. The other thing that you can do is in your compiler, you can write your compiler to give warnings. So sometimes you'll get a message saying, warning, variable foo initialized but never used, right? Or declared but never used. And you know, maybe that's just because you felt like it, or maybe you used to have a use for it, but you don't anymore. But maybe it's because you mistyped what was supposed to be the reference to that variable. So you get that kind of compiler analysis that helps. And then finally, for debugging, there's a lot of information that people have come up with about good debugging techniques. Debugging is still partly an art. And also, one of the best ways to debug your program is to have somebody else debug it. And the reason for that is you know what you meant. If what you wrote down in the program isn't what you meant, you're very likely to read what you meant instead of what you wrote. And so that's why it's good to get somebody else to look at your code. But also, we have this idea of black box and glass box debugging. So given a procedure, one way to debug it is without reading the code of the procedure. Just look at its input-output behavior that it's designed to have and try to figure out sort of corner cases where the spec isn't quite clear about what should happen, or you could have thought of it this way or that way, things like that, or things at the very limits of the domain of your program. So that's black box debugging. See how it does on cases that you think ought to be hard. And then there's glass box debugging, where you actually look at the code line by line and say, let me make a test case that exercises this line. Let me make a test case that exercises that line, and so on. You're supposed to do both of them. You're supposed to do both black box and glass box debugging as the best way to catch bugs. Don't break the old code with a new fix. Who's had that problem in their project? Right? Something used to work, and you broke something, and you fixed something, and then something else that you had already fixed started not working again. Usually this comes from not understanding your program, so that what you're doing is sticking Band-Aids on things. But sometimes it's because of an unclarity in the specification of the domain of the problem. But anyway, you should watch out for that by anytime you try out something in your program, put that test case in a file so that the next bug fix you do, you can rerun all the tests that you've ever done, right, without having to reinvent them to make sure you aren't breaking old things. There's an interesting debugging technique in which you introduce bugs on purpose. So you just pick some random line in your program and make it do the wrong thing. And the point of that is to see whether the code downstream from there catches the problem. So if this line is generating bad data, do you get the error message that you should get, or does your program blow up? Right? Divide by 0 or something. So that's called regression testing. And the most important thing I'm ever going to say to you, so pay attention, debug by subtraction, not by addition. So if you have a bug, that means it's because there's some code in your program that's wrong. And you need to find that wrong code and take it out, as opposed to put in some extra code that detects this case that isn't working and does a kludgy workaround. Okay, and the reason for that is after you've found your first 10 bugs and put Band-Aids over them, you're going to find that you have Band-Aids on top of Band-Aids, and you can't understand your own code. Believe me, I've been there. So it's a little bit like my advice to you about midterm exams and final exams. Remember I said, plan to spend more time reading than writing on the exam? And you sit there and read the question and make sure you know what the question is asking. It's just like that. When you're debugging a program and something isn't working in your program, if necessary, sit on your hands to prevent yourself from changing the code of your program before you understand why you have that bug. Okay? And then remove whatever is wrong. Even if it's 4 in the morning and the project is due in an hour. Okay. What didn't I say? Anything else? Any comments or questions? Yeah.
Why does Microsoft always produce bad options?
Crappy code. Oh boy. It's gotten better, I have to say. The original answer to that question, when they built Windows on top of DOS, is that the bottommost layer of the system was just totally not built for concurrency. And then they threw this kludge together on top of that, and it couldn't work. With Windows NT, they did a complete rewrite, and they hired a guy who actually knew how to write operating systems, and put him to work. And so the blue screen rate went down a lot at that point. I don't know if you go back that far, but NT was way, way better than anything that came before. It does get better over time, even at Microsoft. But there's one set of answers about how especially evil Microsoft is, and it would be fun to talk about that. But I think it's more important to talk about the sense in which Microsoft is like anybody else who's trying to sell something in the marketplace. People don't go out and buy the next version of your software because you say, we fixed 1,000 bugs. That's not going to be good enough to get them into the store or clicking on the internet. They buy the next version of your software because it says, you can have a desktop picture that swirls around as you move your mouse. Right? Right? That sells software. And so basically there's no incentive for companies to fix bugs. And that's especially true if your company is a monopoly. If your only competition is yourself, then there's really no incentive for you to fix bugs. It's just coming up with something flash that'll impress people. So that's basically why. So be a good consumer of software and ask about how many bugs did you fix since the last version. Another question? Yeah. Between software engineering and computer science? Well, computer science is kind of a big tent. Part of what computer scientists do is properly called science. That would be the theoretical computer scientists who sort of figure out how systems work and how to analyze how systems work. Part of what we do is the engineering of software. It's building software. So software engineering as a name is a kind of there was a political movement within the computer science community to pay more attention to software reliability. Now, they like programming languages that tie one hand behind your back because they think that's how to prevent bugs. So, you know, there's a much longer story than I can tell you in a minute. But software engineering, I would say, is a piece of computer science. Is that fair? OK, see you Monday.